So on to solution stoichiometry. That means how many ions are present in solution, basically. So we're going to talk about that in terms of concentration most often. The concentration of solution is the amount of solute, that's the small thing, in a given quantity of solvent or solution. Remember, solution is solute and solvent together. Solvent is just the thing in big quantity. So we can talk about concentration with various units, but by far the most common unit for us to use is molarity. Molarity has the abbreviation of capital M. That's kind of a big deal. Little m means meters. Big M means molarity. So molarity is moles of solute, that's the little stuff, over liters of solution. Not sure why that has an S. That's liters of solution. So moles of solute, the little stuff only, over total volume of solution. That's solute plus solvent liters. What mass of Ki is required to make 500 milliliters of a 2.80 molar Ki solution? Well, to walk through that, we're going to do our little unit conversion. 500 milliliters. I want to get to liters first, so I'm going to put liters on top, milliliters on the bottom. It takes 1,000 of these to make one of those. And then molarity is a conversion factor that we will use often. Just like we've used density, 2.8 capital M really means 2.8 moles of Ki for every 1 liter of solution. If we want 500 milliliters of solution, that's 2.8 molar Ki. That's how we get that. And whoops, it says what mass, and I got to keep going one more step. So then I do one more conversion. 1 mole of Ki weighs 166 grams. Because it says what mass, I'm looking for grams mass. So do that little math, 166 times 2.8 times 500 divided by 1,000. That means it takes 200, hopefully you got the same answer, 232.4 grams of Ki. And what you would do is you put it in a volumetric flask. Actually, let me just stop there. We're going to describe how to make that solution in a couple of slides when I've got a picture. The chemistry shorthand for concentration is brackets. Enclosing that number in brackets tells you it's a concentration number. So the concentration of Ki is 2.8 molar. The concentration of sodium hydroxide is 0.0871 molar. Because both of those are considered soluble salts, we can also make the assumption that the concentration of K plus ions in that solution is 2.8 molar, and the concentration of iodide ions in that solution is 2.8 molar. We can make an assumption that the concentration of sodium ions in this bottom solution is the exact same because they're all 1-to-1, and the concentration of hydroxide is the same, 0.0871. If we had a different kind of ratio, we would have to take that into account, and we will see that. Okay, remember this 2.32. So how do you make a solution of known molarity? For our specific example on that last slide, you take 232 grams of Ki and put it in a solution, put it in a piece of glassware, put it in a volumetric flask is officially what this guy is known for. What's so good about a volumetric flask? It usually has quite a lot of sig figs for accuracy. So you put your solid salt in the bottom, and then you start adding water, because we're making aqueous solutions here, you start adding water to the vessel. Because the solution total, that's solute plus solvent, needs to be our known quantity. 500 milliliters is what our last example talked about. 500 milliliters, if we choose a 500 milliliter volumetric flask, we now have a solution that's 2.8 molar Ki. If we had put 232 grams of Ki in there and diluted it to a total volume of 500 milliliters. We typically know how many moles we want to put in that solution. Sometimes we're asked to calculate what's the concentration of this final solution, Or, like the example we were actually given, we're told the volume and the concentration and asked how many moles are in that solution. We're going to do the forward and reverse of that type of problem a lot. Remember, molarity is moles of solute over liters of solution. So that's why this solution bit is important. It's not put 232 grams and put 500 milliliters of water. No. It's 500 milliliters of total solution volume. You would have too much volume if you added 500 milliliters of water to that. Okay. The EPA mandates that the chromium-3, and chromium-6 content in drinking water be this concentration or less. If a sample of groundwater contains this much chromium in 4 liters, can you drink that water? Where do we start? My initial instructions with our dimensional analysis unit conversion stuff was find the lonely number. Well, all 3 of these kind of look lonely, but this one is not lonely. That's moles per liter. Moles solute per liter solution. Yep, not lonely. That's a decent conversion factor. Let's start with our 4.5 times 10 to the negative 4 grams and convert that into moles so that we can figure out the concentration of stuff that's actually in this groundwater. So this is chromium that's up for discussion, and chromium weighs 52 grams in 1 mole. So that tells me my sample should have, do the math, 8.65 times 10 to the negative 6 moles of chromium in it. That's chromium 3 plus and chromium 6 plus combined. If I'm wanting to know the concentration of chromium in my sample, I can divide that by 4 liters. So that divided by 4 liters, 2.16 times 10 to the negative 6 molar. Compare that to our given quantity of 1.9 times 10 to the negative 6 molar. Which number is bigger? Blue one, red one. Blue one is bigger. No, don't drink that water. Hexavalent chromium, that's chromium 6. Not safe to drink, for sure. Don't do that. The alcohol, ethanol, content in a 10-gram sample of blood from a driver required 4.23 milliliters of this concentration potassium dichromate for titration. Should they be prosecuted for drunken driving? Well, this one has given an equation, and we're going to need to use that equation to convert and figure out if they really should be prosecuted or not. The equation that I have provided you is not balanced. I really think you should try to balance it on your own, but we can't work it without it being balanced. I'll probably ask you a question about how to balance it. If I start with 3 ethanols and 2 dichromates, what are my remaining coefficients? So given that equation, if we try to start with a lonely number, well, it's less obvious here than it is in some samples. This is a conversion factor. Molarity is a combined unit. Milliliters on its own, that seems like a good place to start. 10-gram sample, no, I'm not ready for that yet. I'm going to start with 4.23 milliliters of potassium dichromate solution. 1,000 milliliters are contained in 1 liter. And the reason I need to go to liters is because there are 0.07654 moles of potassium dichromate in 1 liter solution of potassium dichromate. Okay, if I stopped there, that would tell me moles of dichromate But I don't want to know moles of dichromate. I want to know how moles of dichromate relates to moles of ethanol, because ethanol is what the legal limit talks about. The legal limit, we'll pause for a second, is 0.08% ethanol. Your blood alcohol content needs to be less than 0.08% ethanol. So back where we were, we want to go, I wish I had a longer string, we want to cancel out moles of dichromate, and we want to go to moles of ethanol. So that's just pull the coefficients out of the equation. That's a 3-to-2 ratio. And we're almost there. This percent ethanol is percent by mass. So percent by mass means I need to go one step further. 1 mole of ethanol, it's a long conversion, weighs how many grams? Molar mass? You got a number for me? 46 grams. So that will tell me grams of ethanol in this driver's blood. Okay, hold on. So you do that math and you come up with a number that says 0.022 grams of ethanol. Well, this is not percent ethanol. We want to know percent. So we need to divide by the 10-gram sample to get a percentage number. When dividing by 10 grams, we get 0.22% ethanol. And 0.22% ethanol, that is greater than the legal limit. That person should absolutely be prosecuted. In fact, it changes from a DUI type charge to a gross misdemeanor at that kind of level. Don't do that, folks. Don't do that. All right. Enough lessons for today.